Okay, thanks for the invitation, Henry. It's my great pleasure to be here talking about our recent work on high-performance spectral method with applications in chip design and graph learning. First of all, I would like to give a very high-level summary of our recent research work. In the past decades, we have been striving to develop really efficient algorithms for designing nanoscale chips, which may involve tens of billions of elements. As you can see, we are studying problems from circuit modeling to simulation to optimization and verification. In recent years, we realized that some of the algorithms we have been developing for chip design, computer-aided design problems may also benefit other research communities related to data science, machine learning. So that's why we have a few PhD students currently working on related topics and already accomplished some interesting results. So in this slide, I'm trying to give a very high level picture of our work. So it's true that nowadays graphs and networks are becoming increasingly complex. Although in different settings, the graphs may represent different things. For example, in transportation networks, the graph node corresponds to the cities, while the edge corresponds to the roads. In a social network, we use graph nodes to represent people and edges to represent their friendships, right? So there is a common trend for this kind of networks and graphs. That is, they are only getting bigger and bigger. For instance, the social networks are actually evolving every second, while the circuit networks are doubling in size every 2 years. Then an immediate question would be, how can we cope with this massively complex graphs and networks efficiently? This is actually the research focus in our group in the past decade. Since this talk is mainly about data science applications, I'm going to only focus on applications related to data science and try to ignore any applications in chip design. So the first thing we have been doing in the past 5 years is called graph specification. The idea is that given any complicated graph, are we able to find a much simpler graph while still being able to mimic the original graph? For instance, given this original graph, we are able to compute a specified graph while preserving some very important properties of the original graph, such as the structural properties, as well as the properties related to the spectrum of the graph or network. Since I don't want to introduce too many mathematic details here, I just want to let you know that our graph specification work will allow preserving very important graph properties. Okay, this has been shown to be very important for designing many fast numerical and graph algorithms. For example, the problem for solving large partial differential equations, sparse matrices, graph partitioning, data clustering, semi-supervised learning, maximum flow, and graph embedding. So here I'm going to show you a few examples how this specification technique can be used to accelerate our design and optimization process. For instance, when we are dealing with a chip design task, we can simplify the circuit network drastically without impacting the most important circuit properties. Then we are able to quickly design and optimize the circuit given the simplified circuit structure. So this will allow us to tackle very complicated circuit design tasks in a more efficient manner. Another potential application is in graph learning tasks, where people are interested in extracting useful features from the given data represented by graphs. Because our specification technique will be able to preserve very important graph structural properties, therefore the features can still be preserved. Applying any graph learning algorithms on top of such kind of specified graphs will allow you to achieve much faster speed without sacrificing the final solution quality. Another important application is in operation research, where people try to find the maximum flow of undirected networks or multi-commodity flow problems, which are closely related to many optimization tasks. So by specifying the network structure, we are able to achieve much faster convergence and achieve high quality solution for this kind of challenging problems. So the last, not the least application is for solving partial differential equations. As we know, many PDE problems require converting the original physical domain problem into sparse matrices, where the sparse matrices can be further simplified using spectral specification techniques, where we are able to develop really fast solvers for solving this kind of large-scale matrices. For example, using our technique, we are able to solve linear system equations with billions of unknown variables in a very scalable manner. For example, just a few minutes. Okay, so in the following slides, I'm going to only introduce some recent works related to data science. The first one is called graph learning at scale using spectral method. This work is actually motivated by recent theoretic breakthrough in graph learning, which try to use a convex program to solve a graphic lasso problem. So in this image, we try to illustrate each statistical variable by a single variable x. So there are totally 8 unknown variables here. Then we want to construct a graph which can encode the conditional dependence between these unknown variables. For example, if there is no edge between variable x1 and x4, it means these two variables are statistically independent, conditionally independent. So this will allow us to quickly understand the structure of underlying data sets that can be potentially in high-dimensional space. This will be very critical for many machine learning, manifold learning, data mining, dimensional reduction, clustering tasks. However, the traditional convex program can cost a lot. For example, solving a multi-thousand problem may take many thousand seconds. So in our recent work, we leverage our recent breakthrough in spectral graph theorem to develop really highly scalable spectral method for solving such kind of graphic lasso problem, which allows 1,000 times faster speed for learning really large scale problem. The learned graphs will be further leveraged for dimensionality reduction, data visualization applications, as well as applications in neural network training problems. So another recent application of these spectral algorithms is for graph embedding, which aims to convert the original graph data into low-dimensional vector representations so that downstream machine learning or data mining algorithms can be developed based on these low-dimensional vector representations, which will be more efficient than handling the graph data set directly. However, existing methods for graph embedding can be very costly. We propose the graph zoom framework, which allows to embed a graph in a much faster way with improved accuracy based on our recent results in spectral graph theory. So we show that we can achieve over 120 times speed up for embedding the graph with 400 million edges without losing any accuracy. Another ongoing collaboration with University of Notre Dame targets spectral visualization of large graphs. We try to quickly visualize any kind of complicated graph into a 2D screen while showing the clustering information. For example, on the Facebook graph, we can quickly identify the clusters of the nodes which are closely related to each other. So this will help people to quickly understand the underlying data structure, the geometry of the underlying problem, and make some quick decisions. This will also allow people to find important features out of this kind of result. So our ongoing work try to focus on more general graph problems, such as directed graphs and hypergraphs, right? As more and more data science applications are involving graph structured data sets. People are becoming more and more interested in studying graphs with directed edges, or the hypergraphs, which may involve multiple nodes inside a single edge. Such kind of new data formats may allow people to better understand the underlying relationship. However, existing method will be very costly to apply if the graph itself is big. Our approach tries to use spectral method to coarsen the node and edges so that we can extract really compact graph representations that allow much faster algorithm to be developed for the computations of PageRank vectors, which has been widely used for Google search. Also, for computation of statistical distribution of Markov chains, expected commute time, hypergraph embedding, semi-supervised learning. So I'm just showing some of the latest results. I hope we can find some interesting collaborations inside our university, Stevens. Okay, so I think that's the end of the talk. I think I'm spending probably too much time. Yeah. Thank you, Henry.
Thanks very much, Zhuo. Okay, let me try and ask a question. Here, your talk is mostly on graph learning, right? My last question is, so how about image learning? And are the two similar, or you're talking about entirely different approaches?
Okay, so this is actually a very interesting question related to our research. If you think about image or like photos, right? They can be considered as two-dimensional pixels connected by a regular graph. So more specifically, it's a mesh in 2D. So this kind of research developed in our group can be immediately applied to this kind of mesh graphs because it's more specific. Actually, we have strong interest in applying this kind of spectral method for image applications extended to 3D or 4D. Say if we have three-dimensional scans for MIR, or even in a time-dependent manner, we have four-dimensional 3D images, then this kind of applications will be more interesting. So I think there is a very close connection between image applications with our spectral graph methods.